Welcome students. In this video we are going to talk about exponential, matrix exponential, but we will start with something called exponential of operator. Okay, so basically given operator we want to talk about the exponential of something like this. So for up till now we know that you can put given a real number, you can talk about the exponential of such a number, but the thing is here we are going to talk about a linear operator. So basically consider a linear operator t from Rn to Rn. Rn is linear, okay, is linear. Clear? Now, so I will write it here as T L Rn. So it means Rn to Rn. Clear? Now we already know that the operator norm. We can define the operator norm of T is defined as norm of T is nothing but the maximum of mod x less than equal 1 tx. Okay, so t acting on x, that will be a real number. You see, that will be a element of Rn vector. So I am taking the I'm computing the norm of each vector and then we are taking the maximum. Okay, so first of all, why is this valid? Because you see, you remember that norm function, we actually talked about it. It's a Lipschitz continuous function. So basically it's a continuous function, and t is a linear map from a finite dimension to finite dimension. You can actually show that such a thing is actually going to be continuous. Okay, so norm of tx is nothing but a composition of two continuous function, hence it is continuous, and norm x less than equal 1, this is a closed and bounded set, so compact set, right, in Rn. So you see, a continuous function and a compact set attains its maxima, right? So that is the object which you are defining as a norm. Clear? Okay, now we also know that there are some properties of norm. So let's just write down and it satisfies the usual property. So what are the properties? Norm of t, we know that this is always going to be greater than equal 0, and norm of t will be 0 if and only if t equals to 0. So basically it satisfies all the norm properties. Okay, and b, if you have a constant times a norm t, a linear map operator t, then that is nothing but the modulus of k, okay, and the norm of t. Okay, this holds for k in R. Okay, and we also have that the triangle inequality s plus t is dominated by norm of f plus norm of t. This holds for all s and t linear map from Rn to Rn. Clear? Okay, so now you see we will define something. So now this is fine, right? We have to define some kind of calculus of operators. Okay, and to do that, what we are going to do is we are going to first of all define something called a convergence. Okay, convergence of sequence of operators, okay, and this sequence of operators will write it as a linear map from Rn to Rn. Clear? And we want to define a convergence, and in which thing this in operator norm. Clear? Okay, so let's write down the definition here. Definition. So a sequence of linear operators, linear operator tk, clear, in Lrn is said to converge, to a linear operator. Okay, so basically you have a linear operator given to, let's say, t. I am saying that it will there is a sequence tk which converges to t, and when is that happening? That's the question. Okay, linear operator t, which is again in Lrn to Rn. Okay, as k tends to infinity, So basically what we will do is this, we will write it like this. Okay, limit k tends to infinity, tk is t. Yeah, and this convergence is like this. If for all epsilon greater than 0, okay, so for any epsilon greater than 0, there exists a natural number n, natural number, okay, such that after some point, such that for all k greater than equal capital N, one has, you can make it as small as possible. Okay, so how? In terms of norm. So tk minus t should be less than epsilon. Clear? So this is what it means for a convergence. Okay, so whenever, please remember this thing, whenever we are saying a sequence of linear operators converges to another linear operator, what does it mean? It converges. So basically tk minus t, the distance between tk minus t, think of it like that. Okay, that is very small. So and what is in that sense, which sense the distance? So basically it is the norm. Okay, and what is this norm? This is nothing but the operator norm. Okay, operator norm. So basically if you take the operator norm of tk minus t, that should be made, can be made arbitrarily small. So the tail should be sufficiently smaller, that is. Okay, right. So there are some properties, right, which it should satisfy. So let me put it as a theorem. Okay, so for St, which is a linear map from Rn to Rn, and x in Rn. Okay, the first property is that t of x, you see what is t of x? This is an element of Rn. Please remember this thing. So that is your norm. That can always be dominated by norm of t. This is operator norm. Please remember operator norm. Norm of t is operator norm. Okay, and the norm of x. So this is just an Rn norm. Clear? Okay. So how do you prove something like this? Let's just look at the proof. Okay. So proof. Okay. So see. So this should hold for all x in Rn, right? So if x equals to 0, of course equality holds. There is nothing to prove here. Equality holds. Why there is nothing to prove here? Because you see t is a linear map, right? So t of 0 has to be equal to 0. There is no other way. Yes. So 0 and this side also will be 0. So basically 0 is equal to 0. Okay. Now if x is not a 0 vector other than 0, then we define y to be x by norm x. Okay. Why am I defining this? Because if you do something like this, see, since x is non-zero, norm of x is not 0, right? So if you define a new vector y, which is given by x divided by the length, then what happens to y? The norm of y is basically 1. Okay, so then you can use the operator norm definition. Okay, what is norm of t? So norm of t is always dominates norm of t acting at y, right? See, norm of t is t in operator norm. That is nothing but the maximum of t on the unit circle, right? So y by equals to x by mod x is on the unit circle mod. So basically see, norm of y is nothing but 1, right? Okay, so and this, since this is nothing but the maximum of t on norm x less than equal 1. Okay, this is the definition, right? Okay, so this is always dominates t of y. Clear? Okay, since if it is now is always dominant t of y, now that is nothing but, you see, this is nothing but t of what is y? Y is nothing but x by norm of x. Okay, now see, you can think of this as a constant, right? So t of constant times x is c times tx. That's linear map, right? So you can write it as norm of 1 by norm of x, t of x. I can do that, right? Okay, now see what happens is this norm of x is basically a real number, so I can take it out. So this becomes 1 by norm of x, norm of tx, right? Now if you put it together, what happens? Then you have norm of tx is dominated by, if you take this norm here, norm of t times norm of x. Okay, again I am telling you all the time, please remember which is which. This t of x is an element of Rn. So the norm here is in Rn. Clear? This is an operator norm. Let's just call it like this, operator norm. And this is, so let's just call the operator norm as star norm. That will be more suitable. Star norm, right? Okay, so star norm and this is n norm. Clear? So please keep that in mind. Don't get confused here. Okay, so what are the second property which you can actually say? That norm of TS. So basically the composition of two linear this thing operator, right? T and S, composition is TS, that is dominated by norm of T times norm of S. Right? Again, very important, but I mean relatively easy. Okay, so let's quick look at the proof of this. What happens? The proof is, so for norm x less than equal 1, okay, you see we have to look at this T of Sx, right? So that is always dominated by norm of T, okay, norm of Sx. Clear? This is star norm, okay, and norm of Sx is by the 1, it is always dominated by norm of T, norm of S, norm of X, right? Okay, so and since norm X is always less than 1, this is dominated by norm T, norm S. Okay, see, this I am doing extra. This is already done in week 1, but still it's kind of a revision you can think of. Therefore, norm of TS, okay, is always dominated by norm of T times norm of S. Clear? And the third property which we want, because we are going to use this thing, norm of T power K is always dominated by norm of T to power K. Okay, this holds for K equals to 0, 1, 2. So I think you can handle this part. So please do this thing. So this is by induction using 1, using 2, right? So this is always true. Why I did it again here? Because I want these properties. Okay, I want to exploit these properties to define a new thing. So basically we have a new theorem here. Okay, so you see, given a linear map T, linear operator, sorry, T, which is linear operator from Rn to Rn, and a point T naught, okay, positive, okay, the series, so we are basically looking at a series, okay, summation T power K, T to the power K by K factorial, K equals to 0 to infinity, yes, is absolutely and uniformly convergent for all mod T less than equal T naught. Okay, so you understood what I am saying. See, for an operator T, we can define T power K, right? So this is the composition of T with itself for K times. So here also what we are doing is, and we are using the same idea here, and we are defining a new series here, okay? And this series is like a series of linear operator, okay? So basically, and what we are saying is this: if you define something like this, you can actually show that series is absolutely and uniformly convergent, okay? Very important theorem. We are going to use this theorem. Okay, so this is one of the fundamental theorems which we are going to use, okay, to define what comes next, which is the most important thing. So the proof is very easy. So you see, given a T, right? So the norm of T is fixed. Let's say that is A. Okay, then for T less than, let's say, T naught, you have to have uniform convergence, right? So you look at the norm of T power K, T to the power K by K factorial. Okay, this is always dominated by norm of T power K mod of T power K by K factorial. How is this true? You see, we are using 1 and 3. Okay, we are using 1 and 3. One second, sorry, we are not using 1 and 3, we are using this thing B and 3. Okay, so this property B, property of norm, and this 3. Okay, this is 2, this 2 we are using, and we got this. Clear? Okay, So now this norm of t is nothing but a. So this is nothing but a power k, clear, and t is dominated by t naught. So it is t naught power k by k factorial. Okay. Now what is this? You see, if you take the sum, so but sum k equals to 0 to infinity a power k t naught power k by k factorial is nothing but e power a t naught, right? So we can use Weierstrass M test, okay. This series is dominated by a convergent series, okay, absolutely convergent series. So essentially what happens is you can actually say that this series is absolutely and uniformly converges. That will imply that the series k equals to 0 to infinity, okay, t power k by k factorial, okay, is absolutely convergent and uniformly convergent, okay. So that is there. So basically we saw that if you write a series like this, okay, given a linear operator, then of course we can actually say that it is absolutely and uniformly convergent. What we are going to do is this. This is very important. We are going to define the exponential of a linear operator. So let t from L Rn, okay. Then we define e to the power t, okay, the exponential of t. You see, it looks very much like the exponential, right? Okay, so we'll define this exponential of t is nothing but summation k equals to 0 to infinity t to the power k by k factorial, okay. Is this okay? So you see, what we are doing is this, that using this series, we know that this series is absolutely and uniformly convergent, right? So we are using that part, okay, the absolutely convergence part, and we are actually writing a series which looks like this, and we are saying that it actually gives you a new type of operator which we are going to call e power t, and that is nothing but the sum from k equals to 0 to infinity t to the power k by k power factorial, okay. How do you know something like this can happen? Because of the first theorem, because this is absolutely convergence, right? Okay. Now you see, of course, you can use the properties of limit to show. It is easy to see. It is easy to see that e power t, okay, is a linear operator on Rn. Okay, so this is just a property of limit. You can use the limit and you can say, and of course, this is also true. Okay, norm of e power t is dominated by e power norm of t. Okay, you see, this is what we proved here. Norm of e power t is dominated by e power norm of t. Clear? So that's what I wrote. Clear? Okay, fine. Now I will explain to you why we are suddenly interested in exponential of an operator, but this is very important. Okay, that's what I can say right now. Okay, so we'll write down a definition here. Definition. What we are going to do is this: let A be a n cross n matrix. Okay, we know that any linear operator is nothing but a n cross n matrix. So I am starting out with a which is a n cross n matrix, and for t in R we define e power at. This is the definition which we are using. It is nothing but summation k equals to 0 to infinity a power k t power k by k factorial. Clear? Okay, so this is what we are calling as an exponential of a matrix. So this is called, it is called the exponential of a matrix, okay. So if you think of it properly, you see, let's say A is a 1 cross 1 matrix, which basically you can think of it as a scalar, that this actually matches with your e power some constant times t, right? That's what the definition is. Okay, so in that sense it is true. Okay, and there are some properties of this linear transformation. Okay, what are the properties? So the first property, let's write it as a proposition. Okay, if A and B are linear transformations, okay, if A and B, so let me put it this way, if A and B are linear transformations in Rn, okay, and you defining a new function C, clear, which is A B A inverse, okay, then it is very easy to see that e power C, okay, nothing but A e power B A inverse. Okay, let's quickly do this thing. How do you prove something like this? Let's look at the proof. Yes, these propositions are very important. We are going to use it a lot of time. Yes, so e power, let's say C, what is it? It is limit n tends to infinity, okay, summation k equals to 0 to n, okay, A B A inverse whole power k by k factorial, right? So this is nothing but, you see, now if you just write it, you can break it up using matrices, right? You can write it as A limit n tends to infinity summation k equals to 0 to infinity b power k by k factorial times A inverse, right? This is just you see, A B A inverse whole power k is nothing but A B power k A inverse, right? That's what we are using here. Okay, so if you have this, and then it is nothing but A e to the power B A inverse, clear? So that's the different thing. And also please check this part, you have to check it yourself, check it, that if P inverse AP is the diagonal matrix given by lambda j, so basically diagonals are lambda 1 lambda 2 lambda and everything else is 0, okay, this is the matrix, then e to the power at, we are going to use this property again a lot of time, so please remember, P diagonal matrix whose diagonal is e power lambda jt P inverse, clear? Very simple, okay. So you see, you do not have to calculate everything. So basically, let's say if you have if you know that a matrix is a diagonal matrix, then it is very easy to calculate what exponential is, okay, exponential of such a matrix is. Okay, now there is another proposition which we need to prove. Proposition. So what is it? So let's say that S and T are two linear operators on Rn, okay, such that they are commutative, St equals to Ts, yeah, then what happens is e power s plus t equals to e power s times e power t. So please remember this. See, if A is a matrix, n cross n matrix, e power at is nothing but basically a matrix, right? Yes. Now the thing is, if you have but in real number, what happens is e power a plus b, e to the power a plus b is nothing but e to the power a times e to the power b. We can write it like this, right, for real numbers. But since these are matrices which you are dealing with, so basically the commutative property does not work, right? And then what happens is, when is e power s plus t is e power s times e to the power t, e power t, that only works if s and t are commutative. Okay, so let's look at the proof. See, if st equals to ts, okay, so one can write t plus s whole power n is nothing but n factorial, okay, summation j plus k equals to n. This is just a binomial theorem, nothing special. S power j t power k by j factorial k factorial, Okay, this is just binomial theorem, nothing special. Binomial theorem. Okay, right. Therefore, e power s plus t, if you just write it down, what will happen? This will be nothing but summation j plus k equals to n, right? Equals to n equals to 0 to infinity. Clear? S power j t power k by j factorial k factorial. Clear? This is nothing but summation j equals to 0 to infinity. I can write it like this, right? S power j by j factorial summation k equals to 0 to infinity t power k by k factorial. Clear? We can write it like this. If you just break it up, you can just see that this is always true. Clear? Okay. So now you see this is nothing but e power s times e power t. Okay, so we have this. Fine. So this is, I mean, fine. Huh? Okay. So you see, this is actually something. What we used here is something called a Cauchy product. If you are not familiar with this, please check out. I mean, any mathematical analysis book, you can just find it. Okay. So also check this part. Check this part, that e power t whole inverse. Yes. So exponential t is a matrix, right? So exponential of a matrix, the inverse of that is nothing but e power minus t. Okay, right. There are other some. Okay, so that is fine. Yes. So now the thing is, let us look at some examples and how to calculate the exponentials. Okay. So now, how to calculate exponentials. Exponential of a given matrix. Clear? How to calculate this? So let's look at, you see, the thing is we have to go here step by step. So let's check some simple examples. Yes, and then we can use that idea, and we can go for a more complicated examples. Okay, right. So first of all, let's say if A is a 2 cross 2, let's check with 2 cross 2, A minus B, B, A. Okay, then we have to know what is e power A. Okay, we need to know what is e power A. See, the thing is, then calculate e power A. Calculate e power A. Yeah, that's the question. Okay, so now you see, if one writes, so this is the proof. If we write lambda to be nothing but a plus ib, sorry. If we write lambda to be a plus ib, okay, so basically this is a complex number. Okay, then you see a minus b, b a power k. So this is the small trick which we are using. This is nothing but real part of lambda power k, real minus imaginary part of lambda power k. Okay, imaginary part of lambda power k and real part of lambda power k. Clear? Okay. If lambda is a plus ib, you can of course calculate what is lambda power k, right? And you take the real part, imaginary part, that is given by this, right? So we're just writing it down. That's the only thing. Yes. Therefore, if you want to write e power a now I want to calculate e power a, right? Therefore, e power a, what is it? This is nothing but summation k equals to 0 to infinity this thing, right? Okay, by k factorial, of course. Okay, so this is nothing but real part of lambda power k by k factorial minus imaginary part of lambda power k by k factorial. Okay, again imaginary part of lambda power k by k factorial and real part of lambda power k by k factorial. Okay, see, this is there and there is 1 by k factorial, right, for the e power this thing. That's the definition which we use, right? So I'm just writing it like that. I hope this is clear. Now you see what happens is this thing is nothing but, you can write it as real part of e power lambda minus imaginary part of e power lambda. Okay, and then you have imaginary part of e power lambda and real part of e power lambda. Clear? You see, since this is the sum, you can just put everything together and you can just write it like this, right? Okay, so that is there. Now what is this? This is nothing but, if you break it up, this becomes e power a. So everywhere e power a, so I will just write it like this, e power a cosine b, and this is minus sine b, and this is sine b, and this is nothing but cosine. Okay, so what is exponential a? This is given by this. Clear? Okay, now again this is one way of doing some exponential. See, this is not like a straightforward way. Okay, we'll look at many other how to calculate exponential, but this is just an example of some easy calculations. Okay, now another example, let's just look at another example. If let's say A is another 2 cross 2 matrix, A, B, 0, A, right? Okay, then we need to calculate what is e power a. Let's just calculate that. Okay, see, we can write one may write a to be a0 0a plus 0b 0 0, right? So which is nothing but a times I plus a matrix b. Clear? Now check this part, check that a times I and b commutes. There is nothing to check, actually this is trivial, but anyways, it's identity matrix, right? It's constant times identity. Another one is b, so it commutes. So therefore what happens is e to the power a is nothing but e to the power ai plus b, right? Which is nothing but e to the power b is nothing but e to the power this matrix, right? This matrix. Clear? Okay, so you see, e to the power, let's just calculate this thing. E to the power b is nothing but e to the power 0b 0 0. This is a matrix. Okay, so this is, now the problem is this. See, it is identity, okay, plus the matrix 0b 0 0, okay, plus now b square, the term b square, that is going to be 0, right? B cube is going to be 0, so this will actually be up till here. This will be up till here, right? Since okay, let me write it down. Since b square equals to b cube equals to, these are all going to be the 0 matrix. Okay, so this is identity plus the matrix b. Okay, now what is e power ai? This is nothing but e power a. This is easily checked, right? You can just write it down. I mean, identity matrix, nothing is going to happen. It's basically the same thing, e power a, right? And then it is e power b. So this is e power a times I plus the matrix b. Okay, now if you want to prove it properly, it is e to the power a 1 b 0 1. Clear? So proved. Okay, I hope this is clear. This is how